Hi everybody, welcome back to our last application of exponential functions, which are known as the logistics equation. So the problem with exponential growth, in particular population, is that growth is not unlimited in populations. Either there's so many people that can occupy a place, or there's so many resources, only so many resources that can support a given population. So there's usually something limiting the behavior or the amount of people or objects or animals that can inhabit a particular space. So the logistics equation gives us another stab at these type of models. It gives us a bit of more realistic interpretation of population dynamics. So the equation is of this form: A equals m over 1 plus c e to the negative kt. Different books will use different letters, but this is what our book is using, so I'll go with it. So A is known as the amount of the population, and m here in this context is known as the carrying population. Why is it known as the carrying population? So if A equals m over 1 plus c e to the negative kt, think about what happens as t goes to infinity. Well, if t goes to infinity, e to the negative kt, well, if you think about our pictures, for example, this k is always a positive quantity in this case. So this is always going to go to 0 because our picture is going to look like this. And since this is going to 0, notice that A is going to approach m over 1, since this part of the denominator is going to 0. And so when we get to t at infinity, A is just going to equal m. So this is why it's known as the limiting population, because the population can only grow up to that point. So let's look at an example here and see how this works. So a trainee is hired by a computer manufacturer to test a particular model of computer after it comes off the assembly line. So we're given an equation for the learning curve for the average trainee, which is a logistics equation for the number of computers they can test. So the first thing we want to know is how many computers can an average trainee be expected to test after 6 days. So we want to know what happens when t equals to 6. So that's going to be, so for this equation, that's this, we'll have A equals 200 all over 4 plus 21 e to the negative 0.1 t, and we're going to turn that into a 6 for 6 days, and we go and punch that into our calculator. So this will be approximately 12.8 computers, so we can round that up to approximately 3 computers a day. So now, does A have a limiting value? So let's look at that. So that wants to know what happens as t approaches infinity. So again, as t approaches infinity, e to the negative 0.1 t is going to 0. So that means that A is going to approach 200 over 4, since this value part here will go to 0, and this is equal to 50. So 50 here is our limiting value. So notice that the only reason that m here was our limiting value was this is equal to 1. In more general situations, it's always going to be this number divided by this number that will be your limiting value. In this case, 400 divided by 4 will give us our 50. So that's just a quick example of the logistics equation, and that'll be all for exponential functions. The next series of videos will be on logarithmic functions, and we'll see you then.